Section 12.6 is on binomial expansion. If you will remember, binomial is an expression with two terms. Those terms usually are different. And what we want to do is we want to expand those out. So binomial expansion is when you FOIL, you're expanding a binomial. So we're going to do that out and look at the first 5 binomial expansions. And what we're going to do is we're going to keep in mind that anything to the 0 is itself, is 1. Anything to the 1 is itself. So we are going to add in some placeholders here so we kind of get some symmetry going on. So anything to the 0 is 1, so x plus y to the 0 is just 1. But what I'm going to do is I'm going to add in some placeholders. I'm going to say that's also y to the 0, x to the 0, y to the 0, because that doesn't change anything. Those are 3 values of 1 multiplying together. It's just 1. X plus y to the 1 is just itself, so that's going to be obviously 1x plus 1y. But again, I'm going to add in some placeholders. I'm going to have a y to the 0, an x to the 0, and this is really x to the 1, y to the 1. When I FOIL out x plus y squared, I'm going to get 1x squared plus 2xy plus 1y squared. Adding in my placeholders, this is y to the 0, x to the 1, y to the 1, x to the 0. If I expand out x plus y cubed, I'm going to get 1x cubed plus 3x squared y plus 3xy squared plus 1y cubed. Adding in placeholders, this is y to the 0, y to the 1, x to the 1, x to the 0. Expanding these other two out with placeholders gives me 1x to the 4th, y to the 0, plus 4x cubed, y to the 1st, plus 6x squared, y squared, plus 4x to the 1st, y cubed, plus 1x to the 0, y to the 4th. And to the 5th power, I get 1x to the 5th, y to the 0, plus 5x to the 4th, y to the 1, plus 10x cubed, y squared, plus 10x squared, y cubed, plus 5x to the 1st, y to the 4th, plus 1x to the 0, y to the 5th. So I've expanded out the first 5 powers, and I want to start to notice some patterns that are happening here. So if I take a look, I want to figure out what's happening with my first terms, my last terms, and what's going on with the exponents. So if I look at my first terms, notice they all have a coefficient of 1, first of all. Notice the exponent for x always matches the exponent that I was expanding to. So 1 was 1 here, 2 was 2 here, 3 was 3 here, 4 here, 5 here. Notice they continually go up at the same level as n, if this is x plus y to the n. Also, notice those exponents are the same for the last values of y. So your last term is y to the n, your first term is x to the n. So our first term is x to the n, whatever exponent we are expanding to. Our last term is y to the n, whatever exponent we're expanding to. Let's look at the number of terms in relationship to n. When n was 0 here, we had 1 term. When n was 1, we had 2 terms. When n was 2, we had 3 terms. When n was 3, we had 4 terms, and so on. So the number of terms is always n plus 1. So if we have x plus y to the 17th, we are going to have 18 terms in our expansion. Now let's look at what happens to the exponents of x and y as we move across our expansion. So in the first one, I go, or in the second one actually, I go 1 and then 0. My exponents for x here, 2, 1, 0. my exponents for x, 3, 2, 1, 0. If I look at the fifth one, it's 5, 4, 3, 2, 1, 0. So I am always decreasing by 1. So, my subsequent exponents for x decrease by 1. If we look at our exponents for y, I go 0, 1, 2, 3, 4, 5. So my y exponents are increasing by 1 in the same pattern every time. What's happening with our coefficients is actually something really neat. If we look at just the coefficients happening in our expansions, notice the first coefficients are 1, the last coefficients are 1, and they change in a pattern, a symmetric pattern in between. I have a 2, I have 3, 3, I have 4, 6, 4, I have 5, 10, 10, 5. So this is something very famous called Pascal's triangle. This is called Pascal's triangle, and this is formed using or it outlines these coefficients. So you start with 1 on either side. And what you do is your outsides of your triangle always have a 1, and the inside comes from adding the two terms it's in between. So 1 plus 1 here is 2. Outside is 1, in between is a 3, and a 3, and a 1. This is a 4, and a 6, and a 4, and a 1. This is a 1, a 5, a 10, a 10, a 5, and a 1. I can't get it to move, sorry. Well, sorry. And then it's a 1, a 6, a 15, a 20, a 15, a 15, a 6, and a 1. So notice these coefficients here are in the same pattern as the coefficients in our expansions. So this was the coefficient for x to the 0, x to the 1, x squared, x cubed, or x plus y really, x plus y to the 4th, x plus y to the 5th, x plus y to the 6th. And you can expand this triangle out really forever, and you'll always get these patterns. So here's an example of how we can use Pascal's triangle. If I want to expand 8x plus y to the 8th, I can use Pascal's triangle to figure out my coefficients. So I'm to the 8th, which means my expansion is going to have 9 terms in it, and I'm going to be using the 9th row of Pascal's triangle. So following the patterns I observed, my first coefficient is going to be 1. If I expand my triangle out, my next coefficient will be 8, then 28, then 56, then 70, then 56, 28, 8, and 1. My first x term is going to be x to the 8th, then x to the 7th, 6th, 5th, 4th, 3rd, 2nd, 1st, and 0. And y will expand in the opposite direction, so it'll start at 0, then 1, then 2, then 3, then 4, then 5, 6, 7, getting a little scrunched, and 8. So that it is simple as that to use Pascal's triangle. Now, we can make it a little more complicated if we add coefficients to our terms. So all we're going to do in this case, if I want the seventh expansion, I'm going to have 8 terms. I'm going to use the 7th row. So the 7th row is 1, 7, 21, 35, 35, 21, 7, and 1. So I'm going to, these will be my coefficients, 1, 7, 21, 35, 35, 21, 7, and 1. My x is going to increase incrementally from 7, or decrease 7, 6, 5, 4, 3, 2, 1, 0. My y is going to increase, but I'm going to keep my second term is going to be negative 5y. So what I'm going to do is I'm going to have negative 5y to the 0 plus negative 5y to the first plus, negative 5y to the second times negative 5y to the third, and so on and so on and so on till I get to negative 5y to the 8th. So what I then need to do is I need to distribute my powers down to the negative 5 and to the y. So when you do that, you're going to get much larger coefficients here. So my first one will just be 1 x to the 7th because this term is just 1. My second one will be negative 5 times 7 will be negative 35 x to the 6th, y to the first. And then I'm going to start squaring. So I'm going to have 21 times 25 as my coefficient. I'll multiply that out with my calculator. 5 x to the 5th, y to the 2nd, and so on. So what I would like you to do is just try these next two, try to expand those out. The first one's pretty straightforward. The second one, your first term is going to be 3x. Your second term is going to be 2y, and you're doing the 7th row, so those will actually be the same coefficients that I have in the second example there. And these 6 coefficients you can find at the bottom of Pascal's triangle, which I drew for you. And then try and expand those out, and we will stop the video here and we'll do the rest of the notes in class on Thursday.